Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilhem Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good webinar on unleashing autonomous drones for disaster risk reduction, organized by the ITU together with the United Nations Office for Disaster Risk Reduction during the Disaster Risk Reduction Day. This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we are counting on you, the participants, to help create a very interactive session. Without further ado, I would like to introduce our moderator today. Her name is Mr. Esther Kovacs, co-founder and CEO at Drone Talks. Esther, welcome, and the show is all yours.
Thank you, welcome everyone. And I should admit that this webinar is really close to my heart. I think AI-powered drones are really powerful tools, and they did already so much, but the recent developments really can push further the boundaries of these drone applications for a better future and for a disaster risk reduction. And these technologies currently really improve, in my opinion, efficiency in disaster prevention, for mitigation and preparedness, and really contributing to situational awareness and ensuring early adoption and mitigation of these, disasters and hazards. However, the question came to my mind always when I talk about this topic. It's clear we have a lot of advantages of AI-powered drones to support these emergency operations, and why they are not everywhere currently, what can we do and how can we support better as an industry, and how can we do a better job to the more resilient and sustainable society. So in my opinion, we will hear a lot of suggestions and fantastic opportunities from the speakers. So with that, I would like to open our webinar, and I would like to listen as well for the speakers' presentation and understand better myself as well what are the latest developments. I would like to ask Jenty Krishwood, who is the chief of the Global Risk Analysis and the Reporting Section at the United Nations Office for Disaster Risk Reduction, to open the floor. And please start the webinar.
Jenty, we cannot hear you.
Good afternoon, everyone. It's really an honor and a privilege to be here today at this very exciting session on AI for Good on this International Day for Disaster Risk Reduction. I have to say that this is very much a topic very much close to UNDRR's heart, in the sense that we are constantly striving to see how risk information can become more accessible, more usable, and how we can use technology for the public good. And today's session, I think, is a great opportunity to look at not only how technology is being leveraged for disaster response, but also how technology is being increasingly used for disaster risk reduction and early warning. If I may, I'd just like to show a couple of slides to give a feeling of some of the kinds of work, if the technology will allow, of course. Let's see how we're doing. Just to give a taste of some of the kinds of applications around the world. I think today's session is a beautiful opportunity to learn more about how drones are being used in response activities, incredibly important. And we saw that even in the pandemic, where not only were drones deployed in the traditional search and rescue fields, but also to do things like actually deliver medical supplies and vaccination. And this is a growing and interesting area that allows to think of new ways of using information and of understanding how we can better improve the connection between technology and the public good. But at the same time, there are also interesting examples where we see drone technology being integrated with other kinds of analytics, really to help give a view on things like coastal protection in Vietnam, where drone imagery was combined with seafloor modeling, with mangrove cover, and really was able to help develop a more granular and deep understanding of coastal processes and of ecosystems, and also of early warning for flooding. And finally, the third example I wanted to give was an example from Kazakhstan, where essentially drones have been transforming the way that we're able to monitor and give early warning for glacial lake outburst floods, but also give a feeling of the future trajectory of things like climate change impacts on those glaciers. So I think what we see here is incredible scope for a combination of technological and policy and practical approaches to better understanding risks using this technology. So we've got opportunities of communications, we've got opportunities of modeling and forecasting, we've got opportunities of monitoring and detecting. But as we sum up, it's really clear to also, it's really important to also recognize that there are some regulatory and deployment barriers. There are issues of accountability and accessibility, of interoperability. But at the same time, when those are overcome, drones can really play a key and relatively low-cost role in helping reduce this digital divide and making sure that parts of the world that might have struggled to understand some of their land use issues or struggle to have high quality data can deploy this technology and make that data available as part of a multi-hazard, multi-scale risk management approach. At the same time, I think it's important to realize that that data doesn't exist alone. And as we look at the examples we see today, we recognize that those drone images are tools, and they're tools that need to be part of an analytic framework. They don't just tell you the answer, it's got to be analyzed, it's got to fit in to a proper validation and dialogue and continual learning process. Today's session, I think, is a really great opportunity to both mark the International Day of Disaster Risk Reduction, but also to bring together experience from across the public, private, academic, and civil society sectors to really make sure that we're learning from the technologies of drones. We're making sure that they are being applied both for disaster risk reduction, preparedness, response, and early warning. And I very much thank the organizers and the speakers for the opportunity, and I look forward to a very fruitful and creative discussion in today's session. Thank you so much.
Thank you, Janti. That was really great. And I would like to ask first Dr. Dario Floriano, who is a director of the Laboratory of Intelligent Systems and the Swiss Federal Institute of Technology, Lausanne, to open the floor and start his presentation. Thank you.
Thank you very much, Esther, for the introduction. And let me share my presentation here. Great, you should be able to see it now. Okay, my name is Dario Floriano. I work at the Swiss Federal Institute of Technology in Lausanne. It's called École Polytechnique Fédérale de Lausanne. We have been working for the past 20 years on developing the next generation of drones and artificial intelligence. And disaster risk mitigation is one of our driving purposes. Because from a research perspective, it brings a lot of interesting challenges because drones have to fly in proximity of buildings, in proximity of people, in difficult weather conditions, and must be tolerant to disturbances and potential collisions. Now, as it was already mentioned, drones have a lot of potential applications in disaster mitigation, as we can see in this image here. Now, drones are already used today, and for example, inspecting buildings or bridges at distances. Essentially, most of them are quadcopters with very good cameras and stabilization algorithms that allow rescuers to get images of critical areas. But there is much more potential to drones. For example, you may use drones for flying into confined spaces that humans cannot possibly go in, or it's very dangerous, and where other robots with legs or wheels cannot possibly go. Or you could use drones to deliver first emergency kits to people in emergency situations. Or you can even use swarms of drones flying in high winds to maintain radio communication network where all the communication infrastructure is done, or even small swarms of drones that go into buildings. Well, today we'll have a lot of speakers speaking about many of these topics. I will want to focus today on two topics. One is, how can we have collision resilient drones that can go in places that no other flying machines and no other legged robots or humans can go? How can we deliver goods and emergency kits to people in disaster mitigation? And last but not least, how can we have humans in the loops that eventually, at the end of the day, want to control these drones and gather information in real time? They're going to be of some level of autonomy, but humans eventually will have to be in the loop. Now, to get drones into difficult areas, for example, confined spaces, it is interesting to look at how animals do that. Animals like birds and insects that not only fly in the open sky, but also go through narrow passages and go into branches. And what we see is that they change their morphology to adapt to confined spaces, and they can withstand collisions thanks to their flexibility. We do not have to copy these animals into these mechanical designs, but we can take inspiration from this morphological adaptation to design drones that can adapt their morphologies to pass through narrow passages, like in this building, and then use onboard artificial intelligence and vision to fly stably without any GPS information by looking at features on the ground in order to maintain their stability and also know where they are as they fly in buildings. This is work done in collaboration with my colleague Davide Scaramuzza at the University of Zurich, an expert in vision-based navigation. So this is one first way in which we can solve the problem of going in confined spaces. Another way in which you can adapt the morphology, for example, is to have quadcopters that can fold and become like a remote control car. You see here a drone that flies into a semi-collapsed building on the floor, and then it folds up like a sandwich in half, and then it rolls like a car. You can remotely control this drone and gather first-person view of areas where you cannot possibly send a flying drone because it's a very tiny area. Once the drone has completed the mission, it can just go back to the initial landing location, unfold, and fly back to the user or to another location. But what if we are faced with a situation like this, where we have, for example, a lot of rubbles and cables, where maybe there will be a collision at some point, and if the drone collides and then it falls to the ground, end of mission. Then we asked ourselves, how can insects solve these problems? And this is video footage captured by one of my former students, Adrien Briot, who was visiting my colleague Rob Wood at Harvard University and they were filming houseflies flying in very confined spaces. When he brought back this video, I was astonished, because what happens is that these insects, instead of avoiding collisions, they collide into objects, and because of their exoskeletal structure, they can absorb the collision and keep flying. And so we developed a new generation of drone that they have an exoskeleton, and this exoskeleton can freely rotate around the inner propulsion system where the propellers are, so that the drone can encounter obstacles, and the outer skeleton can protect the drone, the propellers, from the collision and continue to fly. And what you can see here is a drone that has no vision-based intelligence control. It simply tries to follow the north using a magnetic compass, and it leverages this exoskeleton to absorb the collision and keep flying without complex control. Now, this drone has been eventually produced by a company, so you see, safe for humans, by a company and called Flyability. And today the drone is used by many rescue teams around the world, including, for example, the French first aid rescue teams. But here, especially here, for example, is a picture of this drone that has been deployed in glaciers to go down deep into crevices where humans cannot possibly go and inspect, for example, if there is any need for people or if searching for people in these difficult situations. Now, this exoskeletal structure can be used also in other concepts. For example, in some situations, you may have people that are stranded in areas where you want to get them either emergency kits or like a mobile phone to communicate with, and you cannot possibly use one helicopter, you cannot possibly use a delivery drone because it's dangerous because of all the propellers. And so here we came up with a new concept of a drone that is protected by an exoskeletal structure and can carry cargo within it. So the drone, you can think of the drone as like the box where you can put the parcels inside. You can essentially imagine the drone is the box. You can close the box around your parcel. The parcel is hanging inside this drone. You see here the drone that has a small parcel, an emergency kit. In this case, they can fly to the hand of a person stranded in a building. And because the propellers are protected, the person can just grab the drone in the hand, open the drone, gets the parcel, then close the drone again, and then send it back. So that's another quite interesting concept. But now, what if you want to fly, for example, in some situations like where there is radioactive substances, and you do not want to send to be very close, and in this case, you do not want to send a quadcopter because quadcopters have very limited flight range. Instead, you may want to send a drone with wings because drone with wings for the same mass can fly twice the distance. But you want to be more agile than typical aircrafts. You want to be, for example, have the agility of birds that can fly through confined spaces by morphing their shape. They can even withstand collisions, and they can make very rapid turns in very short distances, thanks to their morphing wings and their morphing tail. And so we want to achieve drones that have the agility of birds, that have the agility of quadcopters, but the same long endurance of aircrafts. And so we came up with this new drone that can fly like very long distances, like a conventional aircraft, but it can also morph the wings to perform very rapid turns and even withstand very gusty wind conditions. And you may say, hey, what happens if these drones fall on the ground? And so here we took inspirations from winged insects that use another set of wings to upright themselves. And so we are designing our next generation of drones. They do not have morphing wings in this case, but they have this additional set of wings, which are called elytra, that can be used to upright the wing drone on the ground. And then they, again, deploy themselves to provide additional lift that allow these drones to fly longer distances and offset the added mass. And then last, at the end, there will always be human in the picture. And so if you look at the problem of teleoperating these drones and gathering information, it's a very engaging task. It requires a lot of training, as you can see in these drone racing teams, and it's very fatigue. It implies a lot of fatigue. So these operators, they operate for a few minutes and then they get stressed. And so we try to look at more natural way of controlling these drones. And we studied new wearable exoskeletons that can allow naive people, not trained people, to drive these drones with their body gesture. And we can map the body gesture of people that fly as if they were the drones themselves flying in the sky, and controlling these drones while they gather information from the drone's camera through virtual headset. And to make a long story short, here we have a drone that is deployed in a typical rescue situation. You have the human that at this time the hands are free. We can use data gloves to add additional information like takeoff or pinpoint particular areas that the human rescuer can see from the first person view of the camera as the drone flies in the sky. Here we have naive person who is essentially driving this drone. And this, I think, will unleash the next generation of drones, including swarms of drones that can be controlled by a single person to gather information in real time. So I think drones still have a lot of space to be used, and I'm sure that it will make a difference in the future disaster mitigation scenarios. And with that, I stop sharing.
Thank you, Dario. It was a really interesting presentation. During the Q&A part of the webinar, everyone will be able to submit questions regarding this latest development. So the next speaker is Dr. V.I. Kumar, who is the Nemirovsky Family Dean of Pan Engineering, and we'll talk about autonomy for drones in a harsh environment. So the floor is yours, V.I. Kumar. Thank you.
Thank you very much, Esther. It's really an honor to be here. And in some sense, this is a natural follow-up to my colleague, Dario Floriano's presentation, who motivated the case for using drones in disaster response very well. And what we are looking at is focusing more on embedding AI into these drones so that the humans can be freed up to do tasks that they're best suited to. Before I go into this, I want to say a little bit about where I come from. I'm from the GRASP lab at the University of Pennsylvania, which happens to be the oldest robotics research lab in the world. With 18 faculty, 129 PhD students, there are a lot of people working on problems that are related to the theme of this meeting, which is AI for good. I also want to acknowledge that we get funding and support from many agencies in the US. And we also have close partnerships with several companies, some of which have been spun off out of our lab, whose work is very closely related to the theme, again, of this panel. As Dario said, I think aerial robotics research is just starting. There's huge potential. And as we go forward, I like to focus on these 5 words, all starting with the letter S. Our program is about taking drones, making them smaller so they can navigate in complex environments, making them safer so that they can operate close to humans and in close proximity to humans. Of course, smarter, we want to embed the AI into our drones, make them faster, because usually disaster response, disaster recovery is a time-critical mission. And then finally, you multiply the effect of what individuals can do by having them work in teams, and hence the concept of swarms. So again, whether you look at collapsed buildings after earthquakes, or for example, the recent war in Ukraine, or after hurricanes, or you look after nuclear disasters, I think you're confronted with a highly unstructured environment like this. And what you'd like is for drones to be able to reason about this environment and react very, very quickly, providing intelligence to human search and rescue workers. So as I said before, size matters. So we have been developing a range of platforms. These are just 3 different platforms that we now use for field experiments. So on the top is our workhorse. This is the Falcon 4. It's a 4-kilo platform, not exactly small, but with LiDAR, stereo cameras, and an Intel computational suite, we can do all the computations we need in real time, which is very useful, and be completely autonomous without GPS, without radio control. On the bottom, you see smaller platforms, and you scale things down from 1 kilo down to 250 grams to 133 grams. You're now relying on smartphone processors, and with that come essentially constraints that'll come from smaller processors, smaller sensors, and the mission life for platforms like this is also much, much smaller. But we use a whole plethora of platforms. The important thing I want to convey is that all the designs for these platforms and the software stack for these platforms are all open sourced. And I do hope that there are people in the audience would be willing to work to adopt some of these platforms and the software and improve on them as time goes by. There are many benefits of scaling down. I just show a video of honeybees, which you can find on YouTube, and then experiments on the bottom left, which show mid-air collisions between small robots that essentially show that as you scale things down, your inertia goes down, and the max acceleration you can achieve and the basin of attraction for stable flight actually increases. So in the bottom center, you see videos of our vehicles navigating a stream of obstacles without knowing where the obstacles are. So using vision and IMU information, they can bounce off obstacles and able to navigate, in this case, without using external motion capture camera systems, a fairly complex environment. And this is the benefit when you scale things down. It's really hard to do this in larger scales. So some of these we've actually looked at using in nuclear reactors. So this is a picture of me in one of the reactor units in Fukushima. This is back in 2014. And we're basically below the sort of the primary containment vessel. And the question is, could we send drones to explore this fairly three-dimensional unknown environment? And it's a complicated environment, poor lighting conditions, water dripping, high temperatures, radioactivity, and smoke. And we try to recreate these conditions inside our laboratory. Actually, we have a mock-up, a one-fourth scale mock-up of the nuclear reactor where we do these experiments. And the idea then is you use these smartphone-grade processors and sensors to power really small drones, 250-gram drones, to navigate and just collect information. And the idea is once these drones go in, they'll never come out because of radioactivity, they'll be damaged. But they can come close enough to the hatch so that the data can be extracted and operators can then understand what is inside the the reactor. So this was done in collaboration with TEPCO back in 2016, 2017. More generally, though, we want the human operators to be freed of the task of interpreting information in real time. So I want to show you a set of experiments we're doing. This happens to be our campus on the top left. On the top right, you see a semantic map that's built in an automated way from a high altitude UAV. So essentially, you can recognize trees, you can recognize buildings, light poles, cars, and so on. And if you again, using what is now standard computer vision algorithms, you can train the system to recognize objects of interest. So that's the semantic map. But we also are interested in knowing where the objects of interest are. So we're interested in simultaneously collecting semantic information and metric information. This you see in the bottom left. So oftentimes you're covering large areas, but really the information you're interested in is not that dense. So for instance, on the bottom left, you see 2 robot experiments that's essentially gathered all kinds of information about our campus, leaving out information about roads where it's easy to navigate, but retaining information where there are obstacles and where there are trees. And this is done in an automated way. This happens to be done with 3 UAVs. So in all of these, you're trying to maximize the information gathered while minimizing the time taken, and you want to minimize the uncertainty. So we're doing this with a variety of platforms, and I'm going to show you some videos that illustrate this. So this happens to be with a UAV that was flying high, gathering the semantic map, and then 2 UAVs flying at 5 meters, one flying at 3.5 meters. There's no GPS, there's no human control, and the robots are coordinated independently without a human actually controlling them. So obviously there needs to be a communication network, so you can see the robots are pretty close to each other, but we're now working on also in a case where these robots can be spread out so that we don't have to worry about, we can actually spread out over large distances. And the bottom right, you'll see
humans are trapped in a number of...
You'll see a video that actually illustrate how you might use this kind of a system for search and rescue. So on the bottom left, you see the aerial images being gathered in real time. And on the right side, you see the semantic map being generated again in real time. So this is again annotating the image, the map with objects of interest. So for example, ignoring movements of moving trucks in this particular case, but retaining movement of parked vehicles. And the point, although this is about drones, I also want to make the point that there's a lot of information you can get if you have low to the ground robots. These happen to be ground robots, but they could be low flying UAVs as well. And the aerial map semantic map is able then to coordinate these low-flying vehicles in search and rescue missions. So why do you want vehicles at different altitudes? Well, obviously from the top, you can recognize things that you cannot see from the sides. And then from the sides, you get complementary information. So our idea here is to just have a heterogeneous team of UAVs that does all this mapping. And if you play the video further, it also shows that our robots are able to recognize humans and essentially find out where the humans are in this larger map. So let me just finish with one other thought. Again, the main goal in our work is thinking about how we can use all kinds of UAVs for GPS-denied autonomous navigation, but get semantic map. And so one particular area of interest for us is precision forestry. So we want to be able to cover large forests, be able to search them. There's very little GPS, very hard for humans to use line of sight control with radios. And so this almost necessarily has to be done autonomously. So this is not really about disaster mitigation, but we do have, in a larger scheme of things, another disaster that is happening today, which is the gradual degradation of our planet. And this is our way of thinking about how we can build high-resolution maps of carbon distribution around the world, in particular in forests. So let me stop here, and I'm going to stop sharing my screen, and I look forward to questions that you might have. Thank you.
Thank you so much for the presentation. The next presenter is Yan Wan, who's a professor at University of Texas at Arlington, and she will be talking about critical components of future smart cities and Internet of Things networks, how drones can be a critical component of those. Thank you. Yan, the floor is yours.
Thank you. Let me share my screen. Do you see the screen? Do you see my screen or no?
Yes, we can see your screen. Yes.
Okay, great. All right. Okay, so thank you very much. So it's my great pleasure to share with you my research on the networked UAVs for disaster response. So currently we're undergoing the transition to Industry 4.0, which is featured by technologies such as autonomy, big data, AI, IoT, robotics, and cyber-physical systems. And here I have a cartoon from the internet. So this is Society 5.0 in Japan. And you can see the use of the key technologies in diverse applications. For example, the agriculture, healthcare, autonomous driving, infrastructure, and also finance. So in the future society, the robot will be a key component. So in that sense, the UAVs or the drones that we have been familiar with are aerial robots. So they are not simple vehicles. They are aerial robots with integrated sensing, communication, control, computing, and also networking capabilities. And this is a figure from NASA about the use of UAVs in future smart cities. So you can see the diverse use of the UAVs, and one of them is the emergency response. So we have all been familiar with the use of UAVs for applications such as the last mile delivery. And over there, a single UAV is used. And to fully explore the use of UAVs, we can go from the single UAV to networked UAVs. And here, network UAV basically refers to the networking in the air. So the UAVs will be able to talk to each other, to exchange information, maintain safe maneuvering, and also coordination for time-critical missions. You may have also seen the light show like this. So in these scenarios, we have a lot of UAVs, but the UAVs are controlled through a central ground station. And what we're talking about here is the capability for the UAVs to talk directly to each other. So to enable the networked UAVs funded by several SF grants, we have been working on developing an open networked UAV computing system. So the system integrates the plug and play components, including the quadcopter, the controls, the communication, networking, and also the computing. So all of this work together to enable the networked UAVs. And if you are interested in the software hardware designs, we have posted everything into the website, which you can refer to. So now I'm going to talk about some applications of networked UAVs that we have been working on. So this is the application that we have worked since 2013, that was about 10 years ago. So this was the Smart America Challenge initiated by the White House. And over there, we have worked with several companies, including Boeing, MassWorks, and the National Instruments on developing the Smart Emergency Response System. And one of the key components of this Smart Emergency Response System is a UAV carried on-demand emergency communication system. So here's a brief motivation. In the lessons learned from the previous disasters and emergencies is that it is very dangerous to plan emergencies assuming that the communication infrastructures exist. So when the communication is not there, the emergency response operations can be significantly disrupted. So this will require us to use the on-demand emergency system, on-demand emergency communication system. And the existing ones include, for example, the helicopters, cells on wheels, and also amateur radios, which each has some limitations. So this motivates us to develop the new on-demand emergency system that can be quickly deployed and also support the transmission of real-time monitoring videos for emergencies. So this video shows the idea in an emergency or a disaster where the cellular towers are down and also the communication is disrupted. What we can do is to send out the UAVs, and the UAVs go into the air, form the network, communication network in the air, and also provide the communication service to the ground. So this enables the emergency response operations to be carried out. And to realize this UAV-enabled on-demand emergency communication system, there are a bunch of challenges, and some are already mentioned by the previous speakers. For example, the small size of the UAVs, which required us not be able to put heavy devices on board. And also we need the long-range communications for emergency response. And in addition, so there are harsh environment. So the UAVs are doing their own missions. So how to maintain a communication system robustly is not easy. And in addition, we want to have plug and play solutions so that the communication system can be deployed on various UAV platforms for different emergency missions. And the idea that we had is to put direction antennas on the UAVs, and the direction antennas can be selfly aligned with each other despite the movement of the UAVs. So to do that, we use a cyber physical systems approach, which features the co-design of networking and decentralized control. And this is featured by the two directions. So in one direction, the antenna control facilitates the robust communication channel. And on the other direction, the networking provides the communication signals, which serve as a measurement for the control algorithms. So this is a video of how the antennas can maintain the same direction despite the movement of the UAVs. And also, the communication signals is significantly affected by the environment. So this introduces unknown parameters in the system. To address that, we use reinforcement learning to come up with optimal controllers and learn the parameters in the system. So here's our hardware design. So this is a component that we can put on any UAVs that allows the communication over long distance to be established. So we come out with a small board using the advanced computing system that is small and also low weight, suitable for UAVs. And over the years, we have developed multiple prototypes with improved performance for emergency staff to use, including a interface that's easy to operate. Here are a bunch of the indoor and outdoor testings. So here you can see that we have the UAVs separated over a certain distance, and the remote videos can be transmitted to the local UAV despite the UAVs are moving. The UAVs are tracking the people on the ground. The antenna directions can be self-aligned aligned. And we have tested in coastal areas and see that the communication distance can be extended to over kilometers with videos being relayed. We have also worked with emergency teams for testing and also verifying the performance of the system. So we worked with the Denton Fire Department and also the Austin Fire Department for these purposes. So for example, in this video, this is a full city disaster drill. The emergency teams are inside a room, and we send the UAVs to the disaster zone, which transmit the real-time information of the disaster zone back to the room. So the emergency team does not need to leave the room, but be able to figure out the first-hand information of the disaster field and plan the response operations remotely. And this is another video inside the garage where we need to find a victim in a chemical leakage environment. So the UAVs are sent out in the air, which enables the communication system and allows the robot operators to be able to operate the ground robot, and the air robot and the ground robot work together to find the victim very quickly. So here's another application. This was a FRL Swarm and Search AI challenge that we participated in 2019. And the goal over there is to have multiple UAVs search in a mountain area, find the fires, and also predict their spread. So this is an interesting scenario because the UAVs need to coordinate among each other and do very complicated tasks. For example, they need to switch between the missions such as search the fire, fly to the zone, track the fire, and also search the properties on the ground, and also recharging. And while they do these various missions, they also need to consider the constraints such as energy, computation, and also safety. So this requires the UAVs to have the networked advanced computing capabilities. So this is pretty much the end of my talk, and I would like to end with discussing some of the enabling technologies toward the networked UAVs. And so one technology, as I mentioned earlier, is the cyber physical systems, which integrates the tight design of sensing, communication, control, and networking. And the other is AI and machine learning. And I want to mention a special branch of it, that is the reinforcement learning, which has a solid control theory to support it. Because of the uncertainties, the stochastic analysis and efficient uncertainty quantification and analysis tools will be very useful. And we have network settings, so the multi-agent theory, including the multi-agent game theory, will play a significant role and equip the UAVs with improved intelligence. And also the scale is increasing when we have a large number of UAVs. So the complex networks and complex systems theory will be useful to guarantee efficient designs in larger scale systems. So that is all for my talk, and I want to thank my funding agencies for supporting the research, and also my collaborators and the students for contributing to the results. Thank you, and I look forward to questions.
Thank you, Jan. That was a fantastic presentation. And with that, I would like to open the floor for the Q&A discussion of the webinar. I would like all the speakers turn on their cameras, please, but the microphone off for now. And actually, my first question is that we heard a lot about autonomy, and we also heard a lot about different solutions, but in my humble opinion, autonomy is the key for scaling. So I'm just wondering, in disaster response, where we need to react on a lot of unexpected situation, is autonomy really the key, or human piloted drones can react better? I'm just wondering what maybe Dario's opinion on that, or if you have any research or any fact-related information what you can share with us, please, Dario.
Yeah, it's a very good question. Actually, when we started with the project in this activity, we thought, and I thought, that having an autonomous drone is the final goal. But we've been engaging for the past, I would say, at least 6 years in rescue operations with Swiss teams, different agencies in Switzerland. And every year we meet at least once, sometimes twice per year, where we take our drones to their training sessions. And what we realize is that the rescuers want to be in the loop. For several reasons. So they want to know what the drone is doing. They do not want the technology to cause additional problems in case something goes wrong. And they want very often to use these drone technologies to gather information. They think information gathering is the most important thing. So I understood that there must be a human in the loop. Now, there is, of course, a lot of space for autonomy, because at some point, either because the communication goes down, as my colleagues have mentioned, or because there are areas that where the human cannot take the right control, or does not have full access to information to pilot a drone. Some local autonomy is required. So I would say that the key word here is, for the future, is more like shared autonomy, where and the question is, do we have algorithms or methods for sharing this control between the human and the drone in an adaptive way, so that the drone takes over or the human takes over when the right time comes?
Yeah, I cannot agree more. I think it depends on the application. And but Vi, what's your view on this? And what are the key challenges of autonomy, in your opinion?
So my research is focused more on pushing autonomy, only because I think the autonomous robot problem is extremely difficult. And look, there's trillions of dollars now being spent on self-driving cars and other things, and we don't know how to do those. So if you, on the other hand, focus purely on autonomy, there are some interesting applications which only autonomous robots can do. So we have a spin-off company which works in mines. Humans cannot go under mines. So this mine collapse in Ghana recently, I mean, our robots were there, and they went, looked around, came back, and told us where the collapse was. Again, after a nuclear reactor accident, you have to send robots in. And there is no way you can teleoperate or remote control these. So in some sense, to figure out how humans can command these robots at a fairly high level, and then reassure them that they're in the loop because they're the ones who are dispatching these robots, I think that's another way of looking at it. I mean, I completely agree with what Dario says, but I think in addition to that problem, there's also this problem of, how do you tell the human to specify the task at a sufficiently high level, and then robots execute on their own?
I just want to add, if possible, so for emergency teams, like the trust is one thing that they heavily rely on. So they have a lot of disaster drills, which basically just to build the trust that they know where they can go to in emergencies. So for autonomies, like autonomous system definitely will play a significant role, as Vijay mentioned. So the trust is also something that we cannot avoid.
I cannot agree more. And I think social acceptance is also a big part of this innovation, because people need to trust, this solution will really solve the problem. And regarding the autonomy and scaling, what's your view when a solution can scale up for, I don't know, one control center, multiple drones, because autonomy can lead there, right? And I'm just wondering if VI, you have a view on that.
Yeah, I mean, yeah, so you're absolutely right. If you want to cover large areas in a short amount of time, you need lots of robots, lots of drones. I think the big challenges there are ensuring coordination. So to coordinate between the robots, to get them to cooperate, you need communication. And it is really, really hard to ensure a appropriate quality of service and representations at the right level that extend over large areas. It's a bit different in cities where you might, everybody talks about 5G and you can enable, build that infrastructure in. But you go out in a forest, you go in underground mines, you go in hurricane devastated areas, and how do you cover large areas really quickly? So autonomy and figuring out how to manage communication and then have a few human operators control lots of drones. I think this is a whole, very, very fertile area for research and development, and also deployment. I know some of my collaborators in the flying labs in robotics are doing a lot of this. And so, as Dario mentioned, doing field work and search and rescue operations is very important, so we can understand the constraints and then guide our research and development based on the constraints and what is really required in that community.
Thank you. So you mentioned a few keywords like 5G, smart cities, and I think my next question is for Jan, because you during your presentation, you had a few researched regarding those areas. So in cities, what's the difference between 5G and the solution what you just explained? And I also see here a question. Can you please comment on application of UAVs for smart cities? The audience already submitting questions. Thank you so much for it. So I think the first is, what's the difference between those and 5G solution? And also, what are the great UAV applications for smart cities? How do you see that?
Yeah, thank you for the question. So 5G is definitely an important infrastructure, right, for communication system, including to providing the communication for UAVs. So one problem with that is they need to provide the coverage to the low altitude airspace, which incurs a lot of cost. So to enable a large area. So the difference in the solution that we have been working on is that it is on demand. So one thing that we need to emphasize is that, so no matter the 5G or the Starlink, right? So they are all communication infrastructures, and their developments are significant. On the other hand, they cannot replace the importance of on-demand communication. So that can be set up on the spot. So for the other question about the UAVs and also the smart cities, so the picture from NASA, that's not my picture. The picture from NASA that I showed in my beginning of slide provides a vision about the use of UAVs for future smart cities. There are indeed a lot. So for example, the aerial taxis and also the cargo transport, and provides traffic surveillance. So there are a lot of applications where UAVs can be used for future smart cities.
Thank you, Jan. So we're talking about applications, and I think there's a lot of verticals within the disaster response category, you know, as well, where we can utilize drones. And I'm just wondering, Dario, you know, if I want to scale, and I don't want to only talk about uncrewed vehicles, you know, but also robotics, what else a drone can do than fly? I think. What do you think about that, Dario, please?
Yeah, it's an interesting question, because indeed we tend to think of drones like only flying machines, but there is no reason why a drone could not, just like birds or rather insects, land and do some work. And indeed, one of the applications in the future smart cities, especially cities that require infrastructure repairment, is to have drones land, perch, do more than inspection, do work. It's construction, it's repair. And so there is a substantial research these days in what we call multimodal or multifunctional drones that not only fly, but that actually physically interact with the environment. And it's not only at the level of a single drone, but it's at the level of multiple drones. You can have swarms of drones that do collaborative work, for example, to build structure or to repair structure.
No, I cannot agree more. And I think two things comes to my mind regarding that. You know, if we still talk a little bit about cities, there is already existing infrastructure there yet. So in my mind, this new innovation should connect with an already existing infrastructure, not just in cities, but everywhere, you know. And we have areas, you know, where we have obviously less infrastructure, you know, than other areas where we have more. So what do you think? And we also have here a question, but I would like to connect the two. How can we have, or how can we kind of, you know, harmonize already existing infrastructure with these new AI-powered drones to be kind of drive forward, you know, this innovation? But I think both areas, you know, and advanced and less advanced areas, I think, and please, all of you, I see Dario is knocking first, so maybe again, Dario, and after all of you, if you want to share some thoughts about this.
Yeah, I was smiling because it's a very interesting project. We did some time ago a collaboration with Norman Foster, very famous architect. We would say the architect of modern airports, the inventor of modern airports. And he designed some of the largest airports in the world. And then he said, hey, what would it take to make the smallest airport in the world for drones in developing countries? Because you could have drones, as Janet showed to us, that could deliver medicaments to long distances and many other things, but there is no infrastructure. So in cities, you can leverage 5G, you can leverage maybe the shafts of lifts in high buildings for having drones that land there and the goods delivered through the lifts to the different floors. But when you are outside, how do you develop these airports? And Norman Foster came up with a concept called the drone port. That is designed out of materials available in developing countries that serve not only as a place where drones can land and can be unload their cargoes, but it's a place where people meet and they learn about new technologies and they carry their goods and becomes a social place of encounter. So it's a lot of opportunities in that area, I believe.
I can just add one comment about the fact that you know, anytime you plug into infrastructure, it fails when you need it the most. And so GPS is a great example. If I'm in New York City, Zurich, and I'm trying to navigate with my smartphone, it doesn't work, right? And oftentimes you need it when you're in really cluttered urban environments. So that's just an example. But if you just think about the idea of a disaster recovery, you might be in the most sophisticated city with all kinds of, you know, Industry 4.0 infrastructure, but will the infrastructure be resilient? So the question also I would ask is, do we know how to build that resilient infrastructure? And I'm not so sure that we've given a lot of thought to that. So yes, if you have infrastructure, we want to be able to plug into it, but the infrastructure can be very unreliable.
Yeah, please, Jan, any thoughts?
I just want to briefly add that when we talk about the infrastructure, communication infrastructure also is one of it. And for communication, for establishing the communication for UAVs in wild field, it's something that's not easy.
Thank you.
100% agree.
Great. We received another question from the audience about the human recognition. So that's to VI Kumar. They say very interested in the semantic map creation and the human recognition. So they would like to listen applications where those solutions were used already, and that's all. I think if you could share a few.
Sure. I think there are many applications where humans are either bad at doing the task or we don't have enough humans available. So I'll give you a great example. If you look at agriculture or forestry or even mining, you're doing something which is fairly boring, fairly repetitive, and it's actually very difficult to do. So if I ask you to go into a forest and count the number of trees and estimate the diameter, and humans are not good at this. But robots, on the other hand, can be very, very precise at this. Not only that, they can cover large areas instead of just sampling them, which is what humans might do. So those are the kinds of tasks we've been focusing on. And of course, you know, the biggest challenge for the century is climate change. And a big piece of that is understanding greenhouse gas emissions and the amount of carbon we have in the world. And so while, you know, you can, and to me, that's very closely linked to disaster recovery as well. So those are the kinds of applications we target. And I know some of you are interested in our autonomy flight stack and how we do these measurements. So all of these are available open source on our GitHub repository, and happy to share a link to people who are interested.
Thank you. And, you know, just one thought about that we had, I think also, you know, when we talk about risk reduction, if a human don't need to do a job which, you know, can cause unnecessary harm for that human, that's also, you know, risk reduction here. You know, we received another question here, which I really love. What's the biggest wish you have of using drones for emergency and disaster recovery? What's still open and have to be done necessarily? So maybe if Dario, you could start with this, and I think that's one of our last questions for today because we are running out of time. So if just in a short few sentences, maybe Dario, what's the biggest wish you have regarding disaster response, innovation and recovery?
Yeah, actually, one is you must have these drones must be reliable. And reliable is an issue that involves, as Vijay and Ian was mentioning, they were mentioning is software, definitely autonomy, communication. But it's also what we do is a physical resilience as well. We started to scratch the surface of the problem, but there is still a lot of work to do. And the second thing I think is one single drone, because of the limited energetic autonomy it has, is not the solution necessarily. So as Vijay and Ian was mentioning, I think the future is going to be in swarms.
So I'll just say, if there's one thing I could wish for, it's better batteries. And in the last 20, 30 years, people keep saying, well, we're getting better batteries, better batteries. No, they're getting less expensive and they're getting smaller, but the specific energy and specific power has not changed. So in fact, the way we do longer range flights at, you know, for 35 minutes at a time with these large UAVs is because we've switched now to lithium ion batteries, which consequently reduce the thrust to weight. So they're a bit less agile, but they can fly longer. But we're fighting this battle for 20, 30 years now. And if there was a breakthrough in that area, it would change how we think about disaster response.
Fantastic. Jan, if you have any wish or thoughts about this topic, please.
Yeah, I agree with that. So the energy, the communication are very important for the UAVs. And also for the emergency teams to use, like how easy it is to operate is also very important.
Fantastic. They said we have 5 minutes more and we received so many questions in the chat. So maybe one more questions quickly before we go to the networking part is that, yeah, so They talk about, Dario here, a payload of drones for last mile essential items delivery. So I think it's not really, you know, necessarily only about disaster response, but of course in a disaster response mindset as well. But if they want to use AI-powered drones for last mile delivery, is there a payload limit, or what's your experience regarding that, Dario, please?
Yeah, so there is the laws of physics are the limitation here. So in order to carry, so essentially the amount of payload you can carry is proportional to the aerial surface, so how large the wings are, or how large the propellers are, and to the speed of flight, so how fast your drones fly or to how fast the propellers fly. And since the limitation of how fast they can fly or spin is given, essentially if you want to carry larger payload, you have to make your drone larger, which makes it more risky. So the question is really assuming that the big question about the energy that Vijay raised is there. But assuming that you have good energy sources, the question is to have drones that can maybe shift between long-range flight with wings, and then when they reach a destination and they have to lower their goods or land in a precise spot, they can transition into a hovering flight and fold their wings. So I would say we can have morphing drones that can try to achieve the best of the two worlds, but it's going to be a trade-off because of these laws of physics.
You know, regarding trade-off, I received here a few questions about limitations of the drone technology. Maybe Jan, what's your view? Where are we regarding those, and what are the current limitations? What we must solve as an industry and government and researcher bodies and everyone together to succeed? Which are probably the top 2-3 limitations currently?
Yeah, so one is the, with regard to the physical limitations, so one is the payload, right? So as already been mentioned. So with that, we cannot have like high-end or heavy sensors or on board, right? So we need to come up with the solutions with the existing sensors and the low-end sensors to fulfill the complicated missions. That adds to the difficulty to come up with the control solutions or software solutions. So another thing is the computing, right? So as we mentioned, the UAVs are doing complicated missions. The example that I give in the end, in that example, the UAVs need to switch between multiple different functions and also coordinate with the other UAVs. And for such computing tasks, also we need a computing board that consumes significant power. So that's another issue that we need to deal with. Yeah, so and also with respect to the weather, right? So resistance, that's another issue, right? How to fly through the wind field. There are tons of uncertainties there, right? How does a UAV deal with the uncertain environment? That's another challenge.
Thank you. We received another question about air balloons and the longer flight time. So I think maybe I shape a little bit of these questions. Like, can we connect air balloons with drones to operate together? I think that would be my question. And also if we can connect solutions, you know, to provide data or provide solutions to problems. How can we connect those ones, and how can we have longer flight time together, or what can we do? I can see Vijay is nodding here, so please, Vijay.
Well, I can only tell you everything that I've learned about balloons that are not good. I mean, one thing, just to follow up on Dario's simple comment about payload and size. So in balloons, obviously the amount of payload you can carry goes with the volume, which means you really need large balloons to lift payloads. So they're immediately impractical for close to the ground operations in urban environments where you have to have small size. So then can you do things overhead? And so our early attempts to develop autonomy in flying vehicles started with drones back in the days where you couldn't stabilize quadrotors. So this is like 1999, 1998, 99. We found that it was really, really hard to operate even modestly sized balloons with 5 miles per hour winds. So that's the other issue, they get blown away. So most of the balloons, the blimps that you see, they're really large blimps. And then you have the control authority to withstand high winds and operate in harsh conditions. So on the other hand, if the conditions are not that are benign, I mean, they could be part of a 5G infrastructure network. They could be part of a smart city. And I think there's a lot of potential, but small size and balloons don't go together. It's as simple as that.
Thank you. I think it's a really clear answer. Okay, I think I am slowly wrapping up, and I would like to have one more question from all of you. I think we had a lot of takeaway here, and you know, I'm a big fan of implementation, and I saw a lot of projects on the screen when you shared, where you have partners, you're working together, you know, on real life cases. So I am just wondering if you can share what's next. Is there some exciting project coming up where you implement these researches in real use cases? And I think maybe Dario first. What's the next step, you know, to unlock the potential of scaling and using this technology in less fortunate areas, for example, of the world?
Well, there are a lot of questions in there. Maybe I can tell you my take on this is, okay, what's next, at least in my laboratory. Definitely, we are going for drones that do more than simply flying. And so we're looking at drones that have multifunctionality, capable of physically interacting with their environment. The second thing is for the scalability. We have a new project. I think that, you know, swarms are really interesting these days, because drones in themselves are becoming a commodity. We can start to scale them up to large numbers. But as Vijay and Jan has mentioned already, it's not clear how you can coordinate multiple of them, how you can interface one person with a swarm, not a single drone. And so that's something I'm very interested at the moment in the laboratory. We are pursuing projects in that direction.
Yeah, I mean, I agree with Dario. That's I think the most promising logical area for further work. The one other comment I'll make is the importance of recruiting talent to this field. So one thing I've learned over the years is you can have great ideas and you want to do good in the world, but somebody has to pay the bills. And so if you look at the work we started doing on subterranean navigation with drones, ultimately that moved forward because people were willing to pay for information in mines, the mining industry. Likewise, if you want to say, I want to save the forests, ultimately people are willing to pay for that, because if you are a timber logging company, you want data. So I think in the disaster response, so likewise, I'll give you another example. Knowing how many trees you have in an orchard is important, because the insurance companies will pay for that. So this is the thing that I struggle with. I think we're all working on ambitious projects, and to reach out to people who care about this is a little different from reaching out, saying, I want to save the world. I want to do good in the world. Ultimately, someone has to pay for it, and this is the stark reality of deployment. So it's something for us to think about, and more the people that work on these problems, the more progress we'll make. So I'm really glad that you organized this panel, and there are all these questions coming in, which just tells me that there's interest from a wide audience, which is wonderful.
Yeah, I cannot agree more. Yeah, it's very it's our goal to have the solutions being used widely, and so the technologies are in the lab, and we participated in a lot of disaster drills, and it's our dream to have it being used by a lot of emergency teams. And talking about the future directions, I also want to add that when we have more UAVs, the traffic management is also very important, how to maintain the safety of the airspace and also maintain the safety of the ground properties as well.
Thank you so much. And with that, I would like to thanks for the audience attending this webinar session, listening to the fantastic speakers. And I would like to give back the floor to the ITU team. Thank you.
Thank you very much, Esther, for this excellent moderation, and a big thanks to our speakers, Dario, Vijay, and Jen and Genti. Like, you did really a great job, and you're doing a really great job. And as well, we want to thank all the participants for making it such an interesting discussion. We had lots of great questions and great insights today on applications and challenges on drones for disaster risk reduction. We encourage you to check out the AI for Good program online to see more robotic sessions that may be of interest to you. In 2 weeks, we'll have a session on autonomous robots for scaling up the solar industry. We are very much looking forward to engaging with you in our upcoming events. And this is the end of this section and the start of the networking in the AI for Good neural network with the panelists and participants for the next 15 minutes. So see you in a couple of minutes. And now I will give the floor back to Anna for the closing informations. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.